bear with me while I find my channel. So I'm going to put up a couple of circuits on the screen, and then we're going to build this basic diode receiver setup. But first I'm going to talk about exactly what it is that I'm building. Whilst I go back and put a little bit more, I have to have the snack though. So now we're going to start having some fun. But I have something to eat. I'm hungry. I'll be right back. I have some new additions to the lab to talk about. Booyah! We're going to start building stuff. It's enough. It's enough about talking about this stuff. We're going to start building this stuff. (1968). discuss this as soon as I'm done with this snack here. Because it's something here that I was not aware of before. Alright, so what this is a device to help add noise to the input of a tape recorder. Now, I don't have a tape recorder. Well, I do, but I'm not using one. So there's an interaction between this and a tape recorder, because it says right here the other end was to be placed in the input of a tape recorder. Well, I didn't know that. I figured I could just build this diode device and then just listen to the noise and hear this stuff. But when you play it back, you only hear it when you play it back. I mean, I don't know if you can do this digital or whatever. But what we could do, I mean, there's amplifier setups. There's it's similar. This is your crystal radio. Is what that looks like. There's a coil, a capacitor, diode, speaker. I got some speakers now. That actually should be like an earphone thing. So we have to build the amp setup, but I'm probably not going to do that tonight. I'll have to wait till tomorrow. This has to do with picking up low frequencies. What is this? That's an amplifier. They even have that going into a recorder of some sort. I'm looking for the see, there's an amplifier set up. There's some stuff here about improved receivers. Looking for those are filters. Else could be the toroid cores for the teletype. The gyrator circuits we talked about. That's the number 3. I'm looking for simple radio receiver. It might be this. I don't know what L2 is. That's a lot of wire there. The coil that I got looks different. It doesn't have that much wire, I don't think. too bad we couldn't hook this up to the input of a microphone on the computer. And then I can't use the camera. I had a way to do it before, like if I had another signal coming in from somewhere, I could make a note in the display and or somehow. So here they've got a 220 nanofarad to the antenna. Then the diode. Now this is very similar to the Raudive circuit, actually. Except for the fact that the resistance in this setup here is set up differently. We want to find the cutoff frequency to this. The cutoff frequency. Let's see if I move this. If I go, see if we determined our cutoff frequency for the Raudive diode setup, which is on the left here, on the right. There's a 10K resistor, a 2000 picofarad capacitor, and we determined that cutoff frequency was 8 kilohertz. The cutoff frequency equals, it's an RC circuit, so it's 1 over 2 pi times RC. So if we look at our simplified crystal radio, we've got 2.2 nanofarads, I think. Diode. What is combination of R8 and C8 removes any remnants of the carrier wave, leaving only the lower frequency modulation signal. This can be applied to a sensitive earphone. More realistically, an amplifier may be used to boost the signal. N2F. That's 2.2 nanofarads. I think that's probably what that means. Alright, let's figure out what it is. Find my trusty dusty calculator somewhere. What did I do with it? I got a lot of stuff piled up over here. Two calculators, and they both disappeared on me. I just had two of them, damn fucking things. You're fucking shitting me today. Well, you know what? We'll just have to do it the old-fashioned way, I guess. So we have 470K, 2.2 nanofarads. Alright, so we've got .000 2.2 nanofarads. That's millifarad, microfarad, nanofarad times 470 times 6.24. That's 6.28 equals. And we'll take this number, 0.00649, that cutoff frequency, that says the cutoff frequency is 154 hertz. Wait a minute, I forgot something. 2 pi RC, the cutoff frequency. Here. I think the cutoff frequency is listed on this. Well, it's not. I thought it was. Well, oh, maybe it's on this one. I don't know. But that's what I've measured it to be. 154 hertz. Strange. So we're going to use a 10K resistor and a 2000 picofarad capacitor. So my question is, do I have, so alright, so what we're going to do is, I'm going to drop this. And I'm going to go to my lovely workspace bench. I'm going to show you a new toy before I do anything. Well, first, I have a fan. Oh, actually, let me move this over. I'm using I have a fan that I've reworked. I got rewired and whatever. That has metal backing on it. That's going to be used for Peltier cooling. That's sort of been built. I've got speakers that I've made up now. These that have been wired. I've done all the soldering on this, on the back of these things. So I got two speakers. Oh God, I have one speaker now. Alright, so here's the deal with these speakers. Now, as you can see, they're small in diameter, so that means they will work for anything for high frequencies. However, this one here, it's got a little bit of an indentation in it, so it may be a little distorted, but we're going to test and calibrate things. We're not going to do all that stuff tonight, I don't think. This speaker, so what we're going to do is we're going to take, on this speaker, we're going to take this cone off eventually at some point. So we're going to have two speakers, basically the same size, same wattage. Actually, This is either a 10 or a 1 watt. Nominal. It's either 1 or 10 watts. This thing here says 8 ohms, 0.25 watts. That one's 0.25. And this one is 0.1, I guess. 1 watt, a tenth of a watt or something. But I'm going to take the cone off because I want to be able to impart more energy into the speaker and just to do some stuff. We'll put that over there, sort of. And I have a bunch of these 1K pots. These are potentiometers with some knobs and stuff. And what I did was I went ahead and I soldered wires, my little spider's nest, to some various potentiometers and capacitors in here. So that's all done. I've got these supposedly RF chokes that we're going to be putting into the circuit to do some testing with. There's some more chokes here. These are all wire. They got wire around them and stuff. That's some cool bean stuff there. I did my 10 volt battery plugs, which I have not taped up yet. Let's see. I'll just put that. Well, I'll put that on top of that mess. Maybe I won't. Let's put it over here, I guess. The coils. I've got some extra coils. Little round. I don't know what that is. Oh, that's a transformer. I've got some transformers. That's a transformer there. It's pretty cool. I've got another little speaker thing here that I soldered up. Maybe we can hook that up or something. I don't know. Let's see, what's that called? Alright, so let me just get this out of the way. Now, I will give you another little demo of my lab area. These are just wires sticking up, don't worry about that. In front here is an oscilloscope that works. We'll be using that at some point. I've got another radio, and down there, you can barely see it, is a square wave generator of sorts. I have a capacitor up here, a variable capacitor that we can play with. This has an attenuator. It has a 50 ohm input and 50 ohm output, which I gotta try to deal with. This rig down here, this radio, this is a receiver that goes all the way down to 10 kilohertz. And right now there's just a wire on the output of that. It's not plugged in or anything. Buried in the corner over there these are some more stuff that I wired up previously. This is my audio generator that you can see right here. There's some books holding up my shelf. I've got a frequency counter there and a frequency counter here. I have a digital voltmeter and an oscilloscope, and I have another oscilloscope just like this one. I wish I could fix this stupid setup here. It just does not like to stay put. I have another neat little tool for the bench. that it's not connected yet or anything, but I will display that because I'm pretty proud of this little gadget that I paid like, I don't know, $5 for this thing or something. I think it was $5. And I've tested it all out. It works really nice. It is a pulse generator. Look at that baby right there, huh? It'll do plus minus. It'll do pulses on top of the 0 and pulses on the bottom. It'll do square waves, pulses. It's a pulse generator. It's going to be a very valuable tool. As a matter of fact, actually, I was supposed to set that up on this test that we're going to do. I may or may not be able to do that tonight. I don't know. But for right now, what we're going to do is we're going to warm up some test equipment over here. The pulse generator hasn't been broken in more or less by myself. I thought at one point it smoked at one time. But I've since went in there and fixed it or worked on it. I cleaned it up and got things working with it and stuff. And so what we're going to do is we're just going to build a passive circuit. This thing here, this was our voltage voltage supply that we were working on. What is this? That looks like a timer circuit that we were building, which we could probably actually use. We can use that. All we're going to do is we're going to grab, we're going to look in here and see. I don't know what's in this package. There's some stuff in there that we can use to play with. There's some stuff in there. I wanted to go back and visit my generators, my little clock oscillators. Let's see, we'll turn this on. That needs to be turned on somehow. And I don't need the frequency monitoring thing. What I need, if I can get in through all these maze of wires. I know I'm somewhat disorganized now, but at some point, what is that? At some point, things will get better. It's just, I've had to do a lot of building and soldering earlier, and that's why this place is a bit of a mess here. It looks like a Zener. So I'm locating a diode right here. I don't know if you can see that. That's a supposedly a germanium diode. And I don't know as far as the direction. I think the band part is where the dark line is. I think. If we take the diode, see, we could replace. I could put that other. Let's see, what are we doing? Not using. If I use the other, if I had. Oh god, I didn't get my stuff together. So what I'd have to do is build two. It's quite a project. It is quite a project, because I've got to build two sets of amplifier circuits, and one for a reference, and then one for the actual signal, which is where the antenna signal is. But right now I'm just wanting to build an RC circuit, put the diode in, and we've got to find a 2000 picofarad capacitor. And where are we going to get that? So, wires themselves usually contribute anywhere from 5 to 10 picofarads. My meter which doesn't say here. I don't know how far down the meter will go. That says nanofarads there. Let's see if I can do a range. So it reads, that's 0.126 nanofarads. 0, that's 20 nanofarads. 100 nanofarads. 1 microfarad. 10 microfarads. So it will read 0.1 nanofarads. It will read, so 1,000 picofarads is going to be 1 nanofarad. So we have to have a 2 nanofarad capacitance. Now, if I use this meter, which you can't, yeah, right there. This is a meter and it's got numbers and stuff, which you can see the numbers there. I mean, I've got a lot of stuff here. I'm into electronics. I know what I'm talking about. I'm slow, but I'm purposeful and intentful. I know exactly what I'm looking for for an end product. It just takes me a little bit of time to get there, you know. And right now I'm looking for my cables. I don't particularly have cables for this, do I? I had another scope probe I was looking at. Let's remove. That really shouldn't be there. Just throw that on the floor. Let's remove this wiring here. And we'll put that up there, I suppose. Let me gather my equipment now. Let's see, that's an output there. Let's take this cable off. And we'll connect our generator up to the scope here momentarily. We're looking for, that's 1 kilohertz. Wait, let's see, that's 10 times 100 is 1 kilohertz, 2 kilohertz, 5 kilohertz, 10 kilohertz. So we've got the range that we're looking for. Where's the... I was looking at some stuff earlier. Where's the signal? Alright, that's reading 1 volt peak to peak at 1 kilohertz. Let's turn this on. And we will grab this, and we will test our levels and our frequencies. And it's reading close to 1 kilohertz. We can be a little bit closer, I suppose. That's reading 1.012. You can't quite see the frequency counter on there, which is right there. But it's reading close enough for government work. Now I'll go over and measure the level. And it's reading it's reading 0.5. On the 20 volt scale, so it's reading 0.5 volts AC voltage. So that's the average voltage, which is a half a volt. 1 volt peak to peak is a half a volt, so it's reading the average value. So that's good. What I want to do is connect the generator into the generator output is 50 ohms, so I can use this attenuator as our means of controlling the attenuation, so that I know exactly what I'm feeding into my circuits. So I will, what will I do here? We'll take this off, this goes off, and we've got to go through this adapter circuitry business all over again. I had this connected over there with, I don't need that though, do I? What I need, what do I need? See, this was the only one of the problems I had. Really, stuff is everywhere, but see, that comes out of there too, doesn't it? I want to use this attenuator. Why don't I do I take this off? I may have to use this wiring setup. I can disconnect this and this again. Here we go again with this mess. That's actually a nice little cable there, isn't it? I could just use that one cable. Oh, I could actually. I could even probably even move it. Well, I can't move it over very much because I ain't got no room. There we go. So we'll connect this guy up to here. Oh, did I forget a battery thing? I did, didn't I? I got two of them connected. So now I've got a cable, I've got a signal going into my attenuator. We'll come out of the attenuator. And I will grab this guy, which is deciding to be not cooperative with me right now. Let's see, that goes in there, and then I've got this. Where's the other adapter? I could use the, if I use that, that would work. Wait a minute. Just connect this to here. I'm gonna swap this around. These cables are low loss. They're very well protected from extraneous stuff going in. I think that's too short. Why am I using that? I think this is too short, unless if I could put my meter up over there if I had to. There's this, and then we connect that to here. And what we're going to do is I'm going to take my meter and just set it up over here. And move some stuff out of the way. And I can turn this. I should be able to turn this. I can't turn that? Well, I can hook it up to this. And we can go back to our AC voltage on here, which decided to turn off on me for some reason. Now we're reading 0.492, which is almost identical to what we were reading over there. Now I can actually read dBm on my meter, and it will tell me the dBm drop. Now on the attenuator, okay, the dBm, it doesn't drop dBm, it doesn't drop volts, it drops power, I think. I'm not 100% sure, but I think it drops power. I think it's a dBW drop. Maybe we could investigate that and see what happens. So I'll hit the select button. And right now we're looking at -4 dBm in relation to there's a -4 dBm drop so I want reference to 0 dBm on my input. So I will drop this level down if I can. Oh, maybe I've got to go higher. So now I'm reading Now I'm reading 0 dBm. That's pretty close. Now I can use the attenuator. I can remove the meter. I can test the attenuator for dBm drop. And it's a little bit off. It's off by 0.1. I mean, it's relatively close on that on that scale. Now if I do the times 10, Now minus 60 is as far as the meter will go, but the attenuator will drop the signal even lower. And what I'm wondering is, why don't we go to the scope and look at the noise? And to do that, we're going to take this cable and we will take this out. I'll put a T in here. And then hook this back up to this guy, hopefully. Now I can monitor the levels accurately coming out of the attenuator, as well as looking at the input of the signal generator here. All right. Now what I want to do is I want to drop my signal level down in dB so that I can look at the noise level coming out of I want to look at everything. What's coming out of this attenuator as far as frequency and everything is what's going to be going into the circuit that I'm going to build. So I want to make sure that everything's nice and clean. And so I'll start attenuating this thing. And then I'll bring up the level on the scope as far as I can read it. That's a 30. That's a 40 dB drop. And I'm at about 20 millivolts peak to peak. That's a very strong signal. It looks really nice. Let's go to another 10 dB. And I still have a signal level there with no noise whatsoever. We're looking at, let's see, we're at 10 millivolts peak to peak, or 10 millivolts per division. So we're looking at 2, 4, 6? That's 6 millivolts peak to peak. You can't really see it looks like noise on the screen, but I'm seeing a nice clear picture. It looks really good. I see some 60 hertz variance going on in there. Let's drop it down another 60 dB. And I can't quite sync it. Alright, let me go back up here and bring this down to 1 because I don't see a signal at 5 millivolts and I'm wondering why it's not there. I wonder if the other channel, well, I can't even get to the other channel. I don't know why it's not showing up. It's like it's right off the scope for some reason. I might be able to bring this out. And that doesn't seem to work, does it? It's supposed to be a ×5 gain. Well, let's drop it to 50. And that's our 6 millivolts peak to peak. Now if I go to 60, I can't synchronize. Oh, I'm not in normal mode. It's just barely synchronizing. That's about 3 volts peak to peak right there. 3 millivolts peak to peak. And that's a pretty clean sine wave. I'm very impressed that I can see that. And we're down to 60 as far as the meter will go. Let's do another 10. Now, there's I can't synchronize it, and if there's any noise and stuff riding on that, I can't see it. Let's drop it to 80. There's a sine wave there though, and I can see the sine wave, but it's really small. So I can go down to I can even go down to 80, and I can see the presence of something down in there. So I'm happy with this setup here. We'll bring this back up to like 20 dB down or something. And it's reading 20 dB on the meter. It looks good on the scope. Now the only question is putting this output into the circuit that we want to build. We've got to have a 10K resistor. Let me get this wire out of the way. I don't know where my whatchamacallit went. We have to have a 10K, and for that I need a magnifying glass, and is it a 10 or a 2? I think it's a 2. That's a 56 of some sort. My wires and everything should be separated from my components. What's this one here? That's a 2, ain't it? Wait, is this a 10? God, I can't see a damn thing. Pretty sure it's a 2. Oh yeah, I can see the 10Ks in that circuit. What is that circuit? That's a generator circuit, isn't it? Well, I hope I don't have to go look for another 10K resistor. That would be kind of a pain in the ass right now. I might have to. I don't see another 10K resistor. Ooh, what if I get in this box? I think there's a crap load of germanium diodes in here. Oh yeah, there's a lot of them. They just have to be worked on. Someone pulled them out of a circuit. There's a 7905 in there. Shit. Well, you know, I could... I may have to look for a 10K resistor. Shit, what is over here? Oh, I think I may have found one. What is this here? Another 2K resistor. There's a 10K resistor. Alright. Now, the VLF circuit in the, for the VLF circuit for the with the gyrator, that thing has a capacitor. Well, actually, no. This other thing has a capacitor in here. Let me just go there. So let's just look at the web page real quick. There's a 220 nanofarad capacitor in here from the antenna. and that blocks any DC from getting into the circuit. So we could see if we could find that. 220 nanofarads, huh? That's 0.2 microfarads. 0.2 microfarads, or 0.1 microfarad. 0.1 microfarad. Those are 0.001 up there. 0.01. 0.1 microfarads. What do I got here? Is that 10 picofarad? I gotta look up 0.1 microfarad on the thing here. There's another. I can measure a 0.1 microfarad with that meter. So what I could do is we can take this out temporarily. And we can somewhere over the rainbow was I looking for? That test circuit cable. So I'll plug that into... It's not going to go into the meter, is it? No, I've got a problem with that. Shit. How the hell am I gonna... Oh, just a minute. What if I do... Can I do this? Can't do that. I can do this. No. I don't even have to do anything. I can just plug this in. What in the frick is wrong with this? Oh, it's got a transistor tester in there that I didn't know about, but it's blocking my... There is a transistor tester in this thing. You learn something new every day. Why the frick isn't it? It is in there, but it don't go in very good. I'm telling you. Let's go ahead and plug this into here. And we'll go to capacitance. And we want microfarads. Capacitor here somewhere. .15 nanofarads. Ooh, 0.15 nanofarads. Okay, well, I need something bigger than that. I'm not going to get it out of there, am I? I don't know what these guys are here. That's a 0.2 nanofarad. Nanofarad. Someone got parts for building something. These are all like 0.2 nanofarad. I think these are high voltage protector capacitors. 86 nanofarads. Yeah. Well, we're gonna have to dig into the capacitor. Where the fuck am I gonna find that thing? There's something in here. And got another small speaker. This is an even smaller one. Ooh, there's a 1 microfarad. I found me a 1 microfarad capacitor. Now if I can find another one just like it. That'd be cool beans, wouldn't it? I mean, that puts us in the ballpark. We're looking for... What were we looking for? That's a 1 microfarad. I thought we were looking for 1000 picofarads is 1 nanofarad. Two nanofarads. That would be 10 of those other capacitors. I might have that. Let's see what this bad boy is here. So we might be able to use that one. We'll keep that out. That's a 58 nanofarad. These guys are small, aren't they? What did I do with the other ones? Oh, they're in here. Okay, well, I guess we might have to add a bunch of them up for the sake of time and that sort of thing. Let's see if there's something here. There's in this box for goodies. There's this. Ooh, 2200. What is this now? .2 nanofarads. That's what we want. We want 2000s. It's 2200. The capacitance is a little bit high, so that means the frequency cutoff is going to be a little bit lower than 8 kilohertz. So we found we've got 2 of these. So if we use 2 of them, that will bring our capacitance up to 16 kilohertz. What's this guy here? Is that a coil? Oh, I think I found a 2 Henry coil. Just throw that baby out there. There's some stuff in here. That's a diode. A 1N270. What that is. There are some dotted type capacitors. I don't know what they're. Those wires are cut up anyway. What that is. Oh, these blue things are all diodes? One N270. I got a bunch of 1N270 diodes in here. They're easy to spot because they're blue. One N270. If I can use them for anything. Alright, well, we got a couple good capacitors there. Alright, so if I wanted to increase the frequency of the cutoff, I would lower the value of the capacitance. So as it happens, I've got a 2 nanofarad, and I think these ones were, I think it's this orange one. That's a 0.2. Ooh, really? 0.2 nanofarads. And that one is a 2 nanofarad. So we've got a decrease of, what was that? I thought that's a tenth of a value. So if we divide by 10, that means we can bring up our cutoff from 8 kilohertz to 80 kilohertz. And if we cut that in half by adding another capacitor, we can bring that value up to 160 kilohertz, which is a little bit higher than what I wanted. But, so there's our two capacitors. The other capacitor I need is the one for they're saying the one for the shortwave circuit is a lot different, but see the coil, I don't know what the coil value. The only coil that I have for that shortwave circuit is an AM coil, which is this guy. And see, this is your, where the hell did my stream go to? This is your typical AM coil with the core in it and stuff. And we could, that sort of adds like an antenna. So I could probably get away with using this. And we're just going to put this right here. And the other thing that I need is that earphone. And I may have that inside of one of the test equipment or test boxes. I'll show you what that illustrious toy is. I got two of them actually. I should have two of these. I've got this kit. I had one a long time ago, but it got stolen by a bunch of jerks in a fucking apartment. So I managed to get one back. I even have a book with some circuits in there to play with. Here's another, and then this has got the audio transformer. It's got some basic stuff in here. It's got an integrated circuit. It doesn't have batteries. There's the radio coil that you can see here. Right there's a coil. Maybe I could move it up a little. It's got a variable capacitor right here, and your capacitors are all laid out for you. We were looking for, there's 100 picofarad, 1,000 picofarad would be 1 nanofarad, but they don't have that. They jump from there to something else. Now I wonder if, well, if I moved that, I could use this. They've got 2 germanium diodes in here and a silicon diode, cadmium sulfide cell, a resistor, a couple of audio transformers, a speaker. They don't have the earphone thing that I was looking for. That's one of the sets that I've got. These sets usually have, wait a minute, is this? Okay, there's nothing underneath. Usually they have the wires in the side of the box. So I got that kit we can play with at some point in life. And then I've got the other kit, which has a bunch of stuff sitting on top of it, unfortunately. I'm going to try to get it out of here. You have to just pile stuff on top of stuff because I got so much stuff. You know what I mean? So this is the other kit. That's the box for that. That's the 2-in-1. This is the one that has the it's got the stuff right in front, which is pretty cool. It's got the it's got a tuning thing here. That's a capacitor, I think. I don't know. There's another tuning knob. It's got the LED. It's got a selector switch, a Morse code, a light, a speaker, and I did find the earphone piece here. Oh, and there's another one. I don't even know if this has like hardly ever been used. I mean, that looks clean. There's no shit in there. And that right there, you probably can't see it very well. There's a picture of my dad when he was in the military, in the army. So this has a coil. It's got your resistors, capacitors, that sort of thing. All I was looking for was this. That one's got wires on the end of it, and that one's got the plug. So this one's got the wires. That's what I was looking for. And that's got the meter. The meter's upside down. The numbers are right side up, but that's a cute little kit. You know, it's cute. I like it. But we're lucky. We found an earphone, which I can listen to. I know you can't, but I can. And eventually what I will do is I will have a plug that goes from the output of what we're listening to into the computer, and you all can hear the same sound that I'll be hearing. And that is going to be cool beans. That's what I call cool beans. Now let's see if I can put this box back over here, even though it's got so much crap here. I got a bag of stuff here. I don't even know what's in this bag. I have like Christmas every day at my house. Fucking Christmas. Alright, where's that headphone? Right there. I'm just gonna check something on my view screen. Oh my god. Now they're forcing me to update Hangouts. Are you fucking kidding me? Screw you. Go the fuck away. I'd have a right to say whether or not I want to update my shit, you know? I should not be forced to update something. I can just go to my mail. I didn't see anything there anyway. Goodbye. Alright. Back to the drawing board. Alright, we can turn this heater off, I think. Alright, so now the capacitor in the other circuit is what? It's a 2.2. That's the one I just picked out. No, that's a 2 nanofarad. Yeah, that's what, isn't that what this big one is? Yeah, that's a 2 nanofarad. So the big one is for the crystal radio circuit, and the point, where's the 2000 picofarad? Is that the same value? 1 picofarad, 10, 100, 1000. It's the same value. It's the same value as the crystal radio, except the difference is they're using a 470K resistor versus a 10K resistor. So if the resistor goes up, if the resistor value goes up, the cutoff frequency is going to go down. Why do they have the cutoff frequency at 154 Hertz when it's a low-pass filter? I don't understand that. Wait a minute, that's not a crystal radio. But that's not a crystal radio. What is this? Oh God, what is this? Diode detector. And then there's a 220 nanofarad. In front of the diode. I know I did that right. See, it's right there. The capacitor, the resistor is 470K. Right there. I'll do it again. 2000 picofarads is 2 nanofarads. Milli, micro, nanofarads. Wait. Or 2000 pico is 2 nanofarads times 470 times 6.28 equals Did I make a mistake? That's 169 hertz. I don't know. I used 2.2 probably before. That doesn't make any sense because that's going to cut off all the frequencies. What the fuck are they doing? I don't know what they're doing in that circuit. It doesn't make any sense. What the hell? I don't understand what they're doing here. I'll show you the circuit again here. See this C8? This combination of R8 and C8 is going to short circuit anything above 169 hertz right to ground. I'm confused. Confused as hell. I don't freaking know. There's a 1 microfarad. I found a 1 microfarad, didn't I? But that's not an electrolytic. I mean, I could probably use it. That's a 10 in there, probably. Let's see what this guy is here. Actually, I have to use a magnifying glass in order for me to see anything. Magnifying glass. This is a 0.1 microfarad? That's a 0.1 microfarad. That would be... yeah, but that's not an electrolytic up there. Shit. There's a 5 microfarad. Alright, we've got our 10K resistor, we've got our diode, we've got our antenna. My voltage thing is supply things right in a freaking way. Let's put this over here. Maybe we can put this antenna on this side over here. And I will take my scissors and I will cut off some metal here. Double back on this wire. And we'll try to get that fucker in there. I don't want to go in there very good, does it? Oh, I guess I don't need to double back on that wire. I can just put that right in there. Oh, why did I do what I did? Okay. Okay, I've got the antenna in. I need a 200 nanofarad. Why don't I just leave this in here? That means 10 of these guys, I think. I don't have 10 of those. Oh, no, that's a, I need a 200 nanofarad. That's a 0.2 microfarad. We could use the 0.1 that I found, but that's an electrolytic. We'll just skip that for now. We use the diode. No. There's a diode tester on here, but I think I know how to set this up. So that's a diode. Then we've got the RC combination. It's a 10K, and this guy here. Which I can't seem to put anywhere. This thing's taking up all kinds of room on here. Damn it. Got our RC combination. Let's move this diode over. And I will run a ground wire. I guess I could just run it to the other end of that coil. There's no tuning circuit though. Then we'll take the 5 microfarad, that's the minus. And we'll go from diode to here. And we'll take our earphone. I don't have a tuning circuit. I can add that capacitor, and then we can have a tuning circuit here momentarily. I don't even know if this was ever even used. Probably was. This looks brand new. I don't think this has been used. I think somebody bought this for their kids or something. They never used it. Because this earphone thing's not even split apart or anything. So we do one wire. I think I'm going to sneeze. Now we'll see if we can hear anything here. I don't hear nothing. Let's grab this capacitor. And we'll put that in parallel with the coil. I don't hear squat. I think it's because the coil is, let's take this guy, take that off, and we'll measure the resistance across the coil. Okay, it's acting weird. There's no AC voltage on it. Why isn't it reading a resistance? It wasn't connected. Okay, it's connected now. Now the question is, though, can I get everything else connected in there? This thing's gonna screw up again. Damn it to hell. Okay. I don't have enough places to put the wire now. If I'm very careful. I don't hear any noise or anything. What if the diode's backwards? Yeah, I don't hear anything. What if the diode's any good? 0.3 volts. That's reverse biased. That's 0.3 volts. But that's reverse bias, though I'm pretty sure of it. I'm pretty sure the band is in the correct direction. The problem, I think, is with the coil. I need a different coil setup in order for that to work. Or let's try something different here. Let's take this coil out of here. Hey, get this sucker out of the way. Put the diode back in. We've got a capacitor. Wait a minute, this is supposed to be... This was supposed to be over here. Let's grab... Just use this antenna wire. They said to use a wire that was only 4 inches long in the Raudive setup. Right now that's what we've got. This is the Raudive diode setup, except there's a tuning capacitor in there. I'll show it to you here. Shit, something dropped. So, can't see it very well. That's the 2.2, that's the 2000 picofarad or 2 nanofarad capacitor, 10K resistor, and the diode. And this is an output capacitor, which is 5 microfarads instead of 1. And I think I've dropped something, because I thought it felt by my foot. But what was it? I know something fell down here. Oh, there's a piece of wire. There's another piece of wire. Be amazing what I could find down there. Alright, so I'm just going to connect the diode. Wait, why is this earphone's not set up right? This is the antenna. Where's the ground? This is the ground. This wire here, this is not even supposed to be there. I was grounding the input. That might explain why I didn't hear nothing. Now we've got the antenna. There's a wire here. There's no noise. I don't hear nothing. If I put this capacitor. Okay, so what we're going to do is we're going to take the output of the generator now. And we're going to watch the loading effect on the scope. And I'm going to listen to it with my headphones. But where's the ground? Okay, that's the ground. And the input to the sine wave goes to where this is. I just need the adapter thing, I think. There. The signal is the red. This is the ground. And I will attenuate this by considerable amounts here so I don't blow up my eardrums. And the input goes to the diode. hear nothing out of this headset speaker. Let's connect up the piezo speaker that I got. Where did that pizza speaker go? Where did that pizza speaker go? Supposed to tape that up. I didn't finish some of my work earlier. Now, the cutoff on this, as I mentioned before, is 8 kilohertz. I'm getting dust, kicking around freaking dust in my room. I did all kinds of soldering earlier in here. No fan. But I did exhaust the fumes out earlier. Alright, let's see if we can make this pizza buzzer make any noise. That's the ground, that's the input. This is the ground. And I've got a little pizza buzzer there. Let's see what happens. No, still nothing. Well, let's look at the output then. Oh, wait a minute. This is the generator. Shit. This is where I have a problem. I can't look at the output. Because I don't have another adapter. I do have another scope probe that I found in here. That I haven't used. This is a very expensive one. And I don't see the connector. Doesn't this just pop out of there? Yeah, I don't know. I thought that had a BNC connector to it, but I guess it doesn't. Another fail. Let's grab the other cable that I've got. I don't know if this one works. Now see, I don't have another adapter like that one. I'm screwed with adapters. All the money that I spent and the one set of adapters that I need, I don't have. I have to make something. Oh, what's this? I've got that. Is that what I need? Let's see here. See, that doesn't... Oh, yes, that'll work. I can go it backwards. And then I've got to have a male-to-male, though. That's the problem. I'll have to frickin' fudge adapters to get the male-to-male. See, that goes in there. That goes in there. Let's put these adapters back in here. So I can use that. Oh. Oh, I think I've solved the problem. I think I solved the problem here. Because I'm just that good. You know what I mean? So I've got this cable. We're going to go to... Oh, wait. Yes, no. Wait. No, I just go to... Oh, I'm already using that. Shit. I can take that out. And you... Oh, I could just take it all together. I could just put this back in. Take this out. We plug this into here. Oh, see, it's in the back. Oh, no, it's not. It's in the front. Okay. Put that around. There's our handy dandy adapter cable, which is sticking out in the middle of everywhere. And we can verify our signal just by touching that, and it works. And we'll use this as a ground. And the output is going to be across that capacitor. Like so. There's nothing there at all. Oh, wait a minute. Yeah, okay. So why is it being attenuated? The input signal is getting attenuated. There's nothing across the diode. That's why I won't have a signal. I thought it wasn't getting attenuated. That's my input signal. Let's drop the speaker. Let's pull this variable capacitor because I'm not using that. Let's hook up this to here. that gets off a little small. There's more of a 60 hertz hum on there. Okay, there's our signal there. There's our half-wave rectified signal. Okay, so that's all looking good. And that's like cranked. Let's crank that up to 20 millivolts. What is that? 50? 50 millivolts. So that's about that's over 50 millivolts peak to peak. And there's a hellacious 60 hertz coming across on there. I don't know why that would be picking that up. Something's not grounded somewhere. Let's go to, oh wait, that's, we're looking at the top of the RC network at the end of the diode. That's not half-wave rectifying, is it? If that signal is that low, how could it be rectifying? I think it's got to be greater than 300 volts. That's like 150 millivolts. Yeah, it was 500 millivolts going in, wasn't it? We could look at our cutoff. It's supposed to be 8 kilohertz. But I want to look at the output of this capacitor. Alright, I'm at 0 dB attenuation here. That's about 400 millivolts peak to peak. Let's crank this up here. Is that, wait a minute, something's not right. Well, it's close. I don't know, it's weird. Let me just crank this up. And I don't know why that 60 hertz is floating around, but we're going to run the frequency test here. So up to 5 kilohertz, 6, 7, 8. Okay, so we can go back to 1 kilohertz. And what we'll do is we'll take our signal here. Now see, I can't. I don't know if I can switch adapters here. There we go. Okay, I've got my adapters switched out. Now I can take this, and I can couple this in sideways. If I can find the damn ground lug, it's over there. I can't couple it in sideways. What the fuck? I can't do anything. Yeah, I got it coupled. I'm monitoring it. Okay, see, but I have to get this into the meter. Because what I want to do is look for the 3 dB drop. Or the meter just loaded it down. Why did it do that? It shouldn't have done that. Oh, well, it would if it was in that section, I suppose. Oops. Voltage AC. And it's reading 125 millivolts. Oh, there's a major loss in signal. Oh, it's because the diode I'm only going to get half of what I'm putting in. So if that's reading 1.5 volts peak to peak, then I'm only going to get, it should be reading 0.75 volts. I'm only getting 0.3. Well, let's look at the dB drop. Let's see what we got here. I'm at minus 15.8 dBm. So we want to find the frequency at 3 dB down from minus 15.8. So that's going to be minus 18.8. So I got a 2200 microfarad a 2200 picofarad capacitor, so the frequency is a little bit higher or lower, the cutoff. It's around 5 kilohertz instead of 8. Now let's use the 200, wait a minute, 200 nanofarad. What is the one they used in that other circuit? I thought it was, that was a 2 nanofarad. This one's a 200 nanofarad. Oh, but the resistance is higher. That's right. $470K, 100K resistor. That's, is that yellow? I don't think I have. So I got too much going on. I can't figure it all out. Well, I can, but Just too lazy tonight. Boy, oh boy. It's messed up. Either way, I don't understand that input circuitry. I do for the Raudive diode, but I don't understand it for the for the receiver. So if I put that capacitor in, I should be able to get up to 50 kilohertz. So we're at minus 15.9 again. Let's see what... Well, the impedance is going to be different. Let's see what happens here. Yeah, it's flat right there. Let's put this bad boy in there. And you have to use a wire. I like to mess with stuff when it works. But tonight, I don't know, I'm not getting the idea of things working very well. God damn it. Everything's falling apart on me. That's strange. It just took the 1 kilohertz and dumped it right out. Why? Have a bad connection or something? Something ain't right. Something's not connecting. Maybe the capacitor's bad or something. Wait a minute. Oh, I see what's... What the hell? Something's not right. This is not connected right. What the hell? Why is this wire? That's ground. Why is this wire over there? That's why I was getting the hum. The ground was floating. Well, that capacitor's sucking the energy right out, sucking the life right out of everything. Oh, it's even distorting the waveform. Well, okay. I can't use that. What was the other one? I got a 0.2 something. How's this one doing? The capacitor's not doing anything. Oh yeah, it's doing something. Alright, let's measure the dB drop. Okay, we're at minus 6 dBm, and we're looking for minus 9. That only goes to about 8 kilohertz. And that's a decent looking square wave. 8 kilohertz. So if I put another one in series, we should be able to get to 16. Let's see how we do. There's 6 dBm. Oh, that's a nice looking rectified signal right there. That's still the same. Okay, that's weird. It's not even using the resistor. It's not even using the capacitor. It's just dropping due to the resistor. Oh, there's this other capacitor here. Could be causing an issue. That's minus 9. Well, that didn't do anything. Why is it going down? Because all I have is a resistor connected. That's ground. That's the diode. It's just connected across a resistor. It shouldn't. The value should not go down. Why the hell is it doing that? The load? Something's getting loaded. I wonder if it's dropping on the input. Let's take a look at the input. dBm. Right, there's 0 dBm on the input. Yeah, it's dropping on the input. That's what's causing it. That's a 10K resistor. Oh, wait a minute. Where's that? Yeah, it's loaded across. Oh, wait a fucking minute. It's not even loaded. It's only loaded in that attenuator. Well, you know what that means, right? The attenuator is supposed to isolate the oscillator, okay? If I take this out and that's gonna be hard to freaking do that. Put that in there. The attenuator is giving me issues. There's my minus 3 dBm drop. Oh, it's still there. That's a high impedance output, 50 ohms. See, that's a problem. You have to maintain an input of a certain value in order to test the output. That 10K shouldn't be affecting that 50 ohm load. I can monitor the input, can I? Well, it's not the attenuator. That's a good thing. Alright, so let's do this backwards again. So this goes back up to here. And this is the input. And we're going to monitor this with the scope. So that we can monitor the output with just the meter. Now I just have to get the scope connected. and make sure that I have a constant output or a constant input. So let's go back up to 1 kilohertz, and it's set to 0 dBm. Now it doesn't look like it's changing at all over there. What did I do different? I had it connected to that meter. Maybe the meter was loading the input down. The frequency response of the meter. That's got a response of up to 20 kilohertz, I think. I don't know what happened. But right now, oh wait, no, it's going. That's still around 7 kilohertz. And this hasn't dropped. Oh, wait just a minute. Yeah, see, I don't know what the fuck is going on. It's right on the input. Oh, wait a minute. We're measuring across the diode. What if I measure across the resistor? That's -6. And that's -9. I have an AC voltage drop across a resistor as the frequency went up. I can't explain that. I cannot, for the life of me, explain this. No, there's that capacitor. That just doesn't make any goddamn sense. Okay, no resistor. -3 dB. Capacitor. -3.3. I've got a problem somewhere. Unless if it's this cable. Let's take this out. It might be that meter. Now I'm looking at the output. Oops. Why the hell is it jumping? Now I'm going to drop this to 3 divisions. Now see, that's staying perfectly at 3 divisions. And that's at 10 kilohertz, 20 kilohertz. I mean, the frequency's going way up there. I don't know if it's the meter. Let's go up to 10 kilohertz, monitor the scope, and plug this into the meter, and see if it drops. Yeah, it's not affecting that at all. It's not dropping on the scope, it's just dropping on the meter. That's just the frequency response of the meter. That's what that is. That doesn't measure dB, does it? What if I look at this 464? Oh wow, that's a major ass drop. It goes from 0.7 volts to 0.5, but it's not showing up on the scope. Let's see what happens if we go over to here. Uh-oh. Guess what? Guess what? Wait a minute, what? Yeah, I just figured it out. It's the meter. I got 0.726 over here. And at 7 kilohertz, 0.726, it's identically the same. But if I put this, if I measure the voltage on this meter, which is supposed to be such a grand and glorious meter, I'm reading 0.5 volts. It's the frequency response of the meter that's dropping the voltage down. Well, that's sucky, huh? If that's the case, let's plug this into here. And wait until it drops down to 0.5 volts. And let's put back in the resistor. And we'll use that capacitor. This is my, where's my ground? This is my ground. Alright, so now I've got an output, rectified output of 0.361 at, whoops, 0.362 at 1 kilohertz. So let's go and see where it drops. And I'm looking at the output on the scope. I should be looking at the input on the scope. Let's do that. I could look at the output, but I want to monitor the input and make sure that the input doesn't change on me. just take this off. Go to here. Now we've got a good measurement there. Alright, it's starting to go down now. Let's go to... See, we're up to 10 kilohertz, okay, already. I think. That's 1K. That's 10K, and there's no drop. So let's go to 10K. There's a little bit of a drop. That's 100K right there. Now I don't know. I'd have to run in that formula. I got 0.35. Okay, so now I've got to figure out what the 3 dB drop is for voltage. That's harder to do, to figure that, I think. Oh, that's dBm. Maybe that's... No, that's supposed to be volts, not power. Oh, it doesn't matter. The frequency response is screwed on it. So, 3 dB... What change in voltage is going to give me a 3 dB drop is my question. And I don't know how to figure that out. 3 dB drop is half the power. Would it be half the voltage? I lost some freaking calculators. I swear to God, I can't remember where I put my shit, you know? I had this memory fucking thing. I got 2 calculators. I don't know what I did with them. Well, they both fell down in the chairs. Why? I need my book back. Alright, so let's say that the voltage is 1/1. So if I want to change in 3 dB, what's the change in voltage going to be? It's not half the voltage, I don't think. 0.5 divided by 1 is 0.5. The log of 0.5. Wait, let me use the other calculator. So I think this one works better. Wait, is there a log button on here? Log 100. There's 2. The log of 0.5 is minus 0.3 times 20. That's a 6 dB drop. And I'm looking for a 3 dB drop. Wait, maybe that's in power. Power equals voltage times current, though. So I get a little confused. I can't remember this. So it seems like it'd be half of that. So log 0.25 equals well, then it's more than that. Log 0.75 equals times 20. It's like point, maybe it's 0.8 or something. 0.8 equals times 20. That's a 2 dB drop. Log 0.65 equals that's close. 0.65. So if I have a voltage of 0.35, it's going to be a little bit more than half of that voltage. Let's see. Times 0.65 volts. It's 0.65 over 1. So this would be 0.65 over 1 equals x over 350. So 0.65 over 1 is for the cross product. And that's 0.65 times 350. The answer is 227. Okay. So if I clear that, if I go 227 divided by 350 equals wait, that's not right. It's got to be in the other direction. 350 minus 227 is 123. 350 plus 123 is 473. Well, that doesn't make any sense. That's more voltage. It must be 350 over 227. Yep, that's what it is. It's 227. But why is that? Log that's a positive number. That's not right. What the fuck is going on? I hate this. It's supposed to be 227 divided by 350 is 0.64. 0.65 log 0.65 times 20. -3. It's like close. Maybe it's a higher number. Log of 0.714. Log 0.714 times 20. 2.9 minus 2.9. There it is, like 250. The answer is 250. It's close to 250, so that's what I can do. I finally got that figured out, huh? I knew I could figure it out. Just take all day to do it. So we've got 350 here, and as soon as that number reads, it's 250 on my meter up here. As soon as that reads 0.250, then that's our 3 dB drop, and we'll find out what our frequency is. And we're looking at this other bigger capacitor here, 110K. So we just set that to 250, 255. And it's reading about 10 kilohertz. And all I gotta do is hook that up into there. I don't have to monitor this because there's no drop there. Let's see. Where's the frequency? Oh, it's not going to read it because it's half-wave rectified. Or something. Or the level's not high enough. The level's probably not high enough. We're just all messed up all around. What can I tell you? But the frequency is it's up to about 120 kilohertz. Now I should be able to hear that. I should be able to hear that with this headphone. Now I can go back here and drop this input here. And we will go take that off. We're going to look at the output. It's going to be right here. I don't have that capacitor in there. Now I'm going to listen for the tone. Well, I can't hear 100 kilohertz anyway. I had to go back to 1 kilohertz. I'm not hearing nothing. There's something wrong with this meter thing, this earphone. Where's the piezo? Yeah, that. Well, I can't hook a speaker. Well, I could hook a speaker up to it. We'll get some sound going here before I go to bed. I'll tell you that right now. Fuck this shit. I want to hear the ghosts, man. I don't even hear anything out of the piezo. There should be sound there. Where the hell's the speakers? I mean, it's at a low level. Well, this is going to be 8 ohms. That's going to load it down good. Something's going to get loaded down now. That's just beyond the range. You have to have an amplifier circuit to do the rest of that stuff. So we had a problem with the meter. The meter frequency response is not going to give me my 3 dB drop, and I can do it with this. So that's good. That's going to be a good thing. So we solved that problem. That was a major problem, trying to figure that out. The half wave, the diode's working perfect. We're up to 120 kilohertz or something. But this is not a crystal radio. The other crystal radio thing they were doing is with that that chip. I gotta call it quits. There's that chip, that TLO82. These are, I think these are all, are these timer circuits? What the hell have I got over here? Fuck. That's a timer. I got a TLO82 kicking around here. That's a timer. Yeah. There's some coils. What the hell is this chip here? I don't know what that chip is. It's a bold discovery. What if we looked at the output? We've got this going into there. Wait, if I connect this back up here. And connect the scope back up to this guy. And look at our waveform. We've got a perfectly beautiful half-wave rectified waveform. What happens if we change it to a square wave? What's the capacitor going to do? It rectifies, but it leaves the 0.3 volts. I can see the 0.3 volts on the bottom of that square wave. And it's rectifying the positive portion. It's a perfect square wave. Let's look at the frequency response of the square wave. That's 1 kilohertz. That's 10 kilohertz. It looks good so far. Now it's getting distorted. 10 kilohertz, 20 kilohertz. There's a transient in there, which is rather interesting. There's enough information there still, though. That's 50, wait, that's 10 kilohertz, 20, 30, 40, 50. That's right at about our limit of input. But there's some interesting spikes going on in there. I wonder if we take the input waveform and bypass the diode and see what happens to, what's our voltage level? 0.5. It's not that high. Let's bypass this. Wait, here we go. We have to short the diode. Oops. Well, I shorted the diode. That's not going to work. I need to take the input and go to over here. Ah, now look what we've got. Let's drop the input level down. There's a transient response now. At the leading and falling edges of the square wave. And that has to do with the ringing effect of the RC time constant. How long it takes to settle down. It's at 50 kilohertz right now. The higher we go in frequency, the more pronounced the transient response is. If we drop this down to 10 kilohertz, there's still a transient spike there, but it's a lot narrower. It doesn't take up as much space. So if we had a capacitor on the output, like we had before, the 5 microfarad. There was a 1 microfarad. They were using, this is a smaller value. Shit. Where's that yellow one? What if we use, let's use this capacitor. This is the output of the signal, right? Wait a minute. This is the signal. Let's go to here. Alright, you're really being discooperative with me, and I don't like it. Okay, well, I've got a low value capacitor in there. I didn't get rid of that transient response. Let's try yeah, let's try take that one out. Go, this is the negative. I'm having all kinds of issues tonight. That's still there. It's not taking care of that transient response. That's something to do with the RC network. And that can be filtered with the amplifier stage that comes after that. That can be filtered out. So that's where that's coming from. Oh, that's weird. Why is it doing that now? Oh, it's really distorted on the output because of this other capacitor at lower frequencies. That's 1 kilohertz. So that's major distortion there. Because we're talking audio frequencies coming in this Raudive circuit. We're not talking RF frequencies. So that capacitor can't be in there. Oh yeah, look at that. Let's see. Wait a minute, that's screwed up too. Oh, because we're doing a square wave. Oh, that's interesting. Because a square wave is DC. Square wave is DC. What if I used a bigger capacitor? Shit. Take this shit out of here. Where's this at? That's a 60 microfarad. That's a plus on this side here. Let's try a 60. That's really not helping matters any either. That's 1 kilohertz. It's getting pretty distorted. 500 hertz. 500 hertz. The audio information, if audio or whatever information that's coming through there might not be lower than 500 hertz. I'm guessing the low value is going to be 1 kilohertz. And there's enough information there, I think. That's 5 kilohertz. So it gets distorted at lower frequencies. What if we take that capacitor out? Yeah, there's still distortion there. That capacitor is not affecting it. What is affecting that? it's not connected. How could that be distorted? What the fuck is going on now? I only have a resistor in here. Why is it distorted? Oh, it's a square wave. Is the generator? It's 50 ohms. It's a 50 ohm output. I wonder if the generator is distorted on the square wave. Because that's just presenting a 50 ohm load. Maybe the generator's got distortion at low. Well, I'm looking across the diode. No, I'm not. What the fuck is wrong with this? I'm having a problem with the generator. The generator's got distortion. At low frequencies. Huh. Oh, I got problems with everything here. That's bad. Well, I think for all intents and purposes, why is that distorted at 1 kilohertz? I'm not going across the diode. All I'm doing is going across the resistor. Yeah, it's not distorted now. But there's some other shit going in there. Oh, because... Oh, the ground connection. The ground connection wasn't connected. It was connected to the diode. Now let me go back to the diode connection and run that frequency again. Yeah, the distortion's gone. We'll do the square wave again. The distortion's gone. Okay. Now we can run it through the diode. I wasn't grounded. That's twice that's happened to me tonight. It's taken me a whole freaking hour to figure that out. Alright, now I can go down. Oh, okay, so there's no distortion there. Oh, where's the capacitor now? So now we go back to the capacitor and run that across. Now we're running our square wave on the high frequency end. There's 10K. So now the distortion's coming in. Now it's probably working like it's supposed to. And it's half-wave rectified, so that's 100 kilohertz. I can get information out of that. Yeah, and then it falls away. So that's about 80 to 100 kilohertz right there with that capacitor. So this is a good Raudive diode setup. Now I go back to the low frequency again. Set it for 1 kilohertz. Expand this baby out. And there's 100 hertz. It's perfect, and it's perfect for a square wave. Now let's take a look at the output of this capacitor. And look at the sine wave. The sine wave is blocking the DC portion. I mean, the capacitor is blocking the DC where it's rectified. It's just looking like a rectified AC signal. But when I look right across the diode, it's rectified with that 0.7 volts. If I use this capacitor in there, which is a 60 microfarad, it just makes it look like an AC signal. Now let me put this guy back in here. That ain't 0.7 volts, is it? 0.2 volts per division. Yeah, that's 0.3 volts. It's still showing that 0.3 volts across at the end of the capacitor. Let's see something here. I don't know. It's weird. So now, the only thing that's missing, this is the ground. No, that's not the ground. That's the input. The fuck? This is the ground. Now we remove the generator, and we have our Raudive circuit modified to 100 kilohertz. And an antenna, they said, I don't know, 4 feet or something, 4 inches. There's our antenna. And if we look at the scope, at an AC signal, there's residual crap there from somewhere. It might be from the generator. We could probably turn the generator off. Turn that off. Turn this off. That's a 60 hertz hum that's coming across the scope. Let's plug in our antenna. And there's our gain. So our signal, aside from the 60 hertz that's in there, is about 5 millivolts peak to peak. And the AC hum is about 5 millivolts peak to peak. Well, maybe it's a little more than that. It's about 6. Let's see what happens when we put this antenna on. that took a long time to build. See, I can touch the end of that antenna and there's a little bit of a signal gain, but oh god. Holy. Alright, we're at just a minute now. Let's see what this looks like here. There's actually more spikes. There's more. God damn it. There's like some spike stuff going on in there. If I use this capacitor on the output, if I don't use it, what the hell just happened? I don't know, something's happened again. Yeah, the capacitor got disconnected. Let's use a diode. The spikes are not as pronounced if I don't use that capacitor. Those are more pronounced. Let's put in put this yellow guy back in there. So there's that signal. It's about 10 millivolts peak to peak. That doesn't look so bad. So the only problem is the 60 hertz. It's being amplified by all of this extraneous wire that's sticking out here. All of these wires are adding to the amplification of the 60 hertz. So if I take this circuit right here and build up a breadboard and make those leads as short as possible so that the leads don't act like an antenna. Alright, that might work. The other option is to make two circuits exactly like this one and run them both into the comparator circuit that we're going to build, and maybe that will, well, I don't think it's going to, it might cancel the ripple. If we can build the amplifier section that has ripple that's less than we're getting about 8 millivolts peak to peak. And I mean, I don't know if there's noise in there, but there certainly is 60 hertz in there. Now if we were to use well, if I use my body as an antenna, I just use my fingers here and add the end of this to the end of this antenna here. Now I'm increasing the level of the 60 hertz. Maybe you can see that on here. Boom. If if I go reach over where this light is, it's really picking it up, 60 Hertz. Let's see what happens when I turn the light off. Okay, let's put this over here. Let's turn the light on. Oh, the 60 Hertz is coming from that light bulb. That is not a regular light bulb, I don't think. That's one of those AC light bulb things. But it's picking up the 60 Hertz from that. Now, if we go back and look at this again, I see some voltage spikes. There's some voltage spikes in there. Let me grab the end of this and see. What we got here. What was that? Was that the 60 Hertz? Yeah, it must be. It's just quieter. That's a lower frequency. That's not 60 Hertz. Oh wow, there's the 60 Hertz. That's something else in there. There's a lower frequency signal coming from somewhere. Like a, I don't know what that is. Or is that a higher frequency signal? That's a higher frequency signal. Where would that be coming from? Oh, it could be coming from the monitors or something. See, there's no generators running. We're just looking at this Raudive input circuit. What I'm going to do is I'm going to turn off the monitors. I'm still streaming. And I'm going to turn off all the monitors. Get my phone. Turn my flashlight on. And I got one more light in the house. These are not incandescent lights either. They're like fluorescent, the cheap, the expensive fluorescent ones that's supposed to save you power. Now my monitors, my computer monitors are all off. My phone is off. And I want want to turn the light off here in a minute and see what this looks like. Oh, the camera's still working. Oh, that's... So whatever was going on, now the monitors, I can turn the monitors back off. Now I can see some noise in there. Oh yeah, there's noise spikes in there. Those are high frequency noise spikes. Oh, there's some good stuff going on. Hello! So that's filtering out all of the RF energy. And I'm using my body as an antenna. I wonder if I could connect this to... Okay, now here's what I'm doing. Okay, so I am grabbing the light, which has got a lot of metal on it, and that's acting as another antenna to pick up more noise. And there are some spikes in there. There's a lot of noise. There's a lot of interesting information in there that looks interesting. Now, let's see here. I can see the 60 hertz hum. Yeah, everything's riding on the 60 hertz hum, so it's kind of difficult to figure that stuff out, but well, that's cool. So, well, let me turn on the monitors. If I can see how to turn them on and see which one was causing a little bit more of that interference. That one seems to be okay. I wonder if it was that living room light. Uh-oh. This one's... That might have been what was doing it right there. There's that frequency. Let me turn this monitor off again. Well, let me turn this monitor off again. Oh, wait a minute. Let me turn this light off. That's what's doing it, the light. Oh. It's that light bulb. The light bulb is vibrating at a higher frequency. Because it's one of those circular fluorescent light bulbs. Wow. Okay, so like right now, my noise level is my average noise level is around 2 millivolts peak to peak, which is really good, and there's a whole crap load of stuff in there that I can see going on, or more or less. If I turn the light on, now I've got a noise level of 6 millivolts peak to peak. So just by turning that light on, it tripled my noise level. Which I guess is okay as far as running experiments. We'll just have to know to turn that light off. I've got some other light bulbs, and we'll just have to deal with, or I could use a little flashlight. You know, I got an LED light here. Let's see what happens when I affect the LED light. Let's see if that does anything. It's got a laser in it too. Let's see if I can point the laser at the diode. I think there's like voices or something. There's noise. There's something. There's stuff coming in there. It looks like audio frequency stuff. So we solved several problems. We solved a few problems. We figured out that this light right here causes quite a bit more noise. I mean, it's only a small amount. It's only 4 extra millivolts peak to peak. But if we can lose that noise and bring it down to 2 millivolts peak to peak, then, you know, we've accomplished something. Because we need to have an RF, an audio frequency, microwave, radio frequency, quiet spectrum when we're doing these tests, and I got the perfect house to do this in. This place is so quiet. So I got a lot of stuff on there. I think we've got a good circuit. Oh, you know what? Let's put in the Raudive capacitor. Let me see something here. Now there's no capacitor in there at all, so it'll pick up radio frequency waves. It'll pick up everything. And I just lost something. I hit a dial by accident. I don't know what I did. Alright, let's put in the higher value, well, the 2000 picofarad capacitor. If I can see where the hell it is here. Now we've got the Raudive capacitor in there, and it looks like that's actually doing a much better job. It's cleared up a lot of noise, for one thing. Even with the light on, it's lowered that level of noise. There's the level of the light. That's about as much as high frequency stuff that I can get in there. That's 2 millivolts peak to peak with this light on. With the light off, there's considerably less noise. and just the hum frequency, I don't see anything in there. There's no high frequency stuff in there at all, or nothing. There's nothing in there. Now let me grab this antenna and see what we've got here. Now we've got some different things going on here. We've got noise riding on the 60 hertz. There's spikes coming up on the 60 hertz. Because I can't see that. There it is. Oh, that just disappeared. There was some spikes in there, some transients in there. One of them looked like they were moving, and now they're gone. Some weird shit, I'm telling you. I can solidify the waveform so that I can look at things. That's perfect. Now when we run this signal through the amplifier, it should eliminate that 60 hertz altogether. And that's me holding the end of the antenna. If I let go of it, there's nothing there. Let's see what happens when I grab the light. The 60 hertz gets bigger. I can see noise riding on the 60 hertz, but it's way down there. It's in the microvolts. That's the stuff we're looking for. That's high frequency stuff that we're looking for. And supposedly, so maybe we can work between these values of capacitor to add or take away noise. Because I don't like these regular receivers. Their bandwidth is different. That goes down to 10 kilohertz. Yep. So I'm going to turn this off and call it a night. I think it's been a success. We figured out the meter's got a frequency response issue. I can use that meter for level changes, for calibration and frequency changes. I have a pulse generator that we can use the square wave now because we know I wasn't grounded correctly. And we can attenuate that. We know the attenuator works. We'll be able to attenuate the pulse wave. That's going to be our information. That's going to be our calibration wave source. We can bring that voltage way down into the microvolts to see if it will pull that information off of the 60 hertz wave that's floating around in the air and everything else. That's going to be our that's our calibration. That will test the signal to noise ratio of our entire system, and we want to see if we can get a good signal to noise ratio. It would be nice to get anywhere like 60 to 90, you know. That would be really nice. I guess that's it. The Raudive diode circuit. I didn't see any major integration or differentiation problems with the 10K resistor. If you use a higher value resistor, that's also going to add noise. There's a 50K pot that I actually made a wire. I set up a wire thing here. Is this 50K or 500? I think this is a 500. Shit. Nope, that's 50K. So I've got a 50K pot here, and we'll add that. We can add that into the input, maybe. I don't. Yeah, we might be able to. Because my idea is wanting to add noise. But then again, we have to make the leads of the circuit small. We have to figure out a prototype board. I got boards. And once we figure that out, we got to build that JFET amp. That's going to be the next step. We'll build the amplifiers. That's what we're going to do. Yo, I got to call it quits. I think we're done here. I think it was, it's getting there, you know? It's getting there.